We're going to take a little trip back through time here. Oncer Grove, OSGOE. Looking at some numbers here. C4CW, casting 495 celebrities worldwide. I am the host of this show. Just want to go back to, 1994 and 1995. Today is the 27th of November. It's a Wednesday. It's 27 November, 2019 start date. Looking at my notepad here from earlier today, where I took a considerable number of notes here. By the way, thank you for tuning in. If you're true fans of this show, yes, I know ordinarily at this time I'm pretty animated or whatever, but I've been in STEM mode here: science, technology, engineering, mathematics. Working diligently on some projects, just catching up. I want to talk about how in 1994-5, my childhood friend, this is a continuation from where I left off with the previous podcast episode where I was discussing the evolution of mathematics from the time when I was first introduced to the concept of curved space, which, we were told when we were children that space is curved. But when it was really put into perspective for me by a childhood friend of mine who's now a professor of mathematics. And I want to talk about his data set that he used from which to mentor me along with my colleagues and I, 495. And I've been piecing together over time in this, some might call it a memory hole, some extensive notes here. So I'm looking at my shorthand, and I'm just going to kind of wing it and just kind of go through what it is that I wrote down, that is jotted down earlier, actually yesterday. So let's just delve into it. So one of the things that I did was I had to go through a system of fact-checking. And these are bullet points here. And so I actually have written fact-checking because I've heard a lot of different pronunciations of a lot of different mathematical expressions, terms, concepts, principles. And thank goodness, that is God, with the advent of the high-speed internet, which did not exist when I was in high school, one is able to do the deduction. That is, listen to different pronunciations of said terms, terminology, expressions, and so forth, etc., and really kind of get a frequency analysis of what is the most common. So in fact-checking and going back and piecing it all together, is bullet point 2. There are people who pronounce, now I was told that they're called Banach Spaces, Banach, Banach Spaces. Somehow, some way, in the Mandela effect of it all, some have come to refer to Banach Spaces as Banach Spaces. Now, I understand you're probably thinking, come on, Grove, it's just a slight, deviation, and it's nothing, considerable. Well, it may seem that way, but if you're familiar with Lagrange, I have heard professors of mathematics actually use the expression Lagrange. And I thought to myself, well, that sounds odd because my math mentor, he would say Lagrange, but then I hear these math professors talk about Lagrange. But we'll get back to that. So, discrepancies in pronunciation. This may seem boring to you, and I completely understand. But if you just kind of follow me for a moment, I'll bring it around full circle. So my math mentor, I'm looking at 1-2 pages of information, see if there is a, you're probably thinking, well, you ought to know, like, how many pages of information. Well, I'm also analyzing Cryptos, and I found what I believe to be an underlying key to the system, and I'm attempting to use it to decipher what is currently undeciphered. So we'll talk about that later. But it looks like there are 2 pages, like 1.5 pages of information. My math mentor, he would often talk about the same set of principles, concepts, theorems, and so forth. So I'll just kind of read down these lists here. There are 3 columns, kind of, sort of. So probability spaces with him was an important because he's a probabilist. He's one of America's foremost probabilists. And he's traveled the world as a lecturer, mathematician, lecturer, and he works in the realm of probability. So probability spaces is a big part of what he would often discuss. And when I looked up probability spaces today, I found that probability spaces refers to a 3-tuple system. So that's 1, 2, 3, the number after 2, 3-tuple. The more I investigate, explore hyperspace, hypergeometry, the multiverse, I realize that the systems of mathematics, though some believe to be abstract in nature, they seem to be woven into the very fabric of our universal matrix. Now, that may seem woo-woo and it may seem outrageous, but I really do believe that with regard to concepts such as probability spaces, these 3-tuple systems, that they are part of our natural existence. So probability spaces, we can expand and expound on that at a later time, but just knowing, generally speaking, that probability spaces was one of the key concepts that was often discussed back in 1994, 1995. Now, keep in mind, let's see, what does this say? A lot of concepts for someone in their early 20s. What does this say? Average math. So imagine you're an average math person, which I was, back in the early 1990s. Graduate of high school. And so you're familiar with basic math, basic algebra, basic geometry, some basic calculus. And then you have a friend who is operating at the advanced level of mathematics, and he happens to be a roommate of yours, and earns his master's, and then shares advanced topics with you. Well, over the course of those are several years, I would often hear about these and learn of these different concepts, principles in math at the advanced level. So probability spaces, important in the field of probability, obviously. And then I would hear about Bernoulli. I would hear about Euler. I would hear about Lagrange. I would hear about the fundamental theorem of calculus, rate of change. I was introduced to, now those all for those of you in the world of math, and or those who have kind of just looked at math topically and haven't explored math at an advanced level so much, but are familiar with perhaps Bernoulli, Euler, Lagrange, rate of change, calculus, pretty standard. Then I was introduced to the concept of FTL, faster than light travel. Mind you, my math mentor is one of the world's foremost probabilists, so he was most certainly way ahead of the curve. And FTL, faster than light travel, which back then seemed very esoteric, somewhat outlandish, very theoretical in nature, is now quite mainstream. When we're considering thinking about faster than light travel, some people to this day believe that faster than light travel is highly theoretical, highly improbable, unlikely, not real, can't be done, might be possible, but again, kind of a stretch of the imagination. Well, now it's pretty much consensus that time travel is for real. We live in a multiverse. There are copies of ourselves. And so in that, tachyons, which have forever been, at least in some context, elusive in the minds of mainstream society, are for real. Similar to the Higgs boson, which is for real. Previously theoretical. Tachyons are said to travel backward in time. And FTL, faster than light travel, involves tachyons. So I was introduced to the concept of FTL, faster than light travel, particles and other types of natural phenomena back in 1994-95. I would also often hear about Hilbert space. Mind you, I am familiar on some level with the concept of Minkowski space versus Newtonian mechanics. I would often hear about Fourier analysis, the Heisenberg principle, which is interchangeably known as the uncertainty principle, Brownian motion. And then I have a diagram here that I have flowcharted where from Heisenberg principle, i.e. / uncertainty principle, there is a line arrow pointing to conjugate properties, bell curve. Bell curve is standard deviation. And then under Brownian motion, I have bijection, or bijective, injective, and surjective, because in calculus, not only do we observe rate of change, but other phenomena. We look at displacement, area, volume, and other. We're talking about integration. We're talking about under the graph, the area therein. Let's see. What are these other notes here? Not everyone will use this stuff. Yeah, so that's the other thing, is back in 1994-95, I was out of high school then, and it was stated by educators at the time that most folks would never be using these maths. They were unimportant. And so there wasn't really a focus on these maths, these intermediate to advanced topics, if you had studied basic to intermediate mathematics in high school. And even if you studied some advanced topics, which back then were calculus was considered advanced back in the 1990s. I don't know what high school you would attend where you would learn of FTL, faster than light travel, concepts such as tachyons. But if you had a professor who discussed, as I indicated, Hilbert space, Fourier analysis, the Heisenberg principle, which is the uncertainty principle, you would still nonetheless often hear that math at the advanced level, calculus and beyond, most students would never ever use those maths, that form level of mathematics, beyond high school, and that it was merely theoretical, in a lot of ways abstract and non-applicable. Whereas today, you still hear some of that, and sometimes a lot of that, but these more previously theoretical and abstract topics are very much applicable, especially with regard to quantum mechanics, which we'll get to in a moment. So keep in mind also that in 1994, 1995, there was a lot of alcohol and a lot of marijuana flowing in the atmosphere, in the ether, in the ebb and flow of the universe, in a vacuum, quantum vacuum that is. So I wasn't focused back then 100% at all times. So looking at this information now and thinking back, I had to piece it all together. And full disclosure, at some point when I had completed half of a college mathematics degree program, I was at that juncture, a college English honors student, which qualified me to begin teaching even then. So I had the opportunity of entering into a teaching program, and I taught English, math, science. I taught algebra 1, 2, geometry 1, 2, and some pre-calculus and calculus. So, but before that, it was parlor room game nights, hanging out with the fellas, listening to lectures, dissertations by my college, pre-college, and then later college math mentor, who's now a professor of mathematics. So he would also talk about the Mandelbrot set and fractal geometry. Let's see. It's going back up here. So Banach Spaces, which some pronounce differently. Josephson sets, which relate to super conducting. And then you would hear the expression Jacobian. Displacement. I've talked about that before. Now, when I communicated with Professor Ronald Mallett, some will say Millett, Ronald Mallett, at the University of Connecticut, he, in terms of his time travel project program, he talked about displacement, which is important when we're talking about time and displacement of time, divergence, similar to the John Teeter story, whether you believe it or not. Amplitude is displacement. And so people who are not math privy, they will hear either displacement or amplitude, and they don't often make the connection that they are one and the same. And in that, there is the phenomenon of fuzziness, which my math mentor back in 1994, 95, prior to I even knowing of Ronald Mallett, some say Mallett, professor, that is, he talked about fuzzy logic. Fuzzy logic. There's also the concept of area and boundary problems. And then we have here, in terms of algorithms, we have nodes, we have branches, we have trees, we have forests. Now, I took a course that I was privileged and honored to have been able to have taken through Princeton University, and I learned of an algorithm known as union find. Now, the way I remember union find is through the Mandela effect. And when I say that, what I mean is, of all the algorithms in the world, imagine this. Now, this is going to sound outrageous to some people. This is going to sound crazy. It's going to sound preposterous. Totally absurd. But follow me on this. Imagine that time travel is real. Michio Kaku And a lot of other leading scientists, physicists say that time travel is absolutely for real. Hugh Everett III knew that it was real. I know that it's real. Ronald Millett knows that it's real. Professor, that is, and Professor Michio Kaku. A lot of leading scientists, mathematicians, physicists, experts, and others believe and know that it's real. Imagine that if you don't believe that it's real, or even if you do, that you're a time traveler. So you travel through time in a hypothetical scenario. And let's say your memory is somehow blanked out, or it's partially blanked out, and you only have partial memory. Well, if you were to remember of the various theorems and equations, myriad theorems and equations, multitudinous equations, theorems, and so on. If there were just one algorithm that you remembered because you're a time traveler, I'm just saying, hypothetically, just bear with me and go out on a limb with me, a stretch of the imagination. Let's say you time travel to another hashtag that is hashtag Other America. So you end up in an Other America. And let's say maybe you're back in time before the advent of the high-speed internet. And let's say they don't create the internet in 1969 at the Department of Defense. I'm just saying, as explorers, as scientists, as analysts, as thinkers, contemplators, futurists, tinkerers of whatever reality, right? We're thinking, contemplating, considering information, possibilities, probabilities. Imagine you time travel like any TV show, movie. Sliders, Quantum Leap, Stargate, Atlantis, SG-1, you name it. You travel through time. The movie, Deja Vu. There's so many movies, so many TV shows, so many books. Ray Bradbury, Sound of Thunder. You travel through time, and you end up in some Other America, where the internet will not be created in 1969. You have some recollection when you come to, because your memory is scrambled. But you come to, and you have some foggy, hazy recollection, some hours, minutes, days, seconds down the road, after you're living in this Other America, possibly having traveled through a Kerr black hole, or by whatever means, contrivance, contraption, Doctor Who-esque reality, excuse me, Project Pegasus, what have you, Rainbow, Project Sign, Project Looking Glass, you name it, you're a time traveler. The TV show, series, travelers, you end up in another, that is Other America. And because of divergence, that is this slight deviation, discrepancy, difference between your point of origin and where you travel, there is no internet created in 1969. And if you were to talk about any type of future knowledge that you have, you would be considered a motherfucking lunatic, an insane, babbling, idiot, buffoon, moron, imbecile, crazy, fucked up person. Because they would be like, we don't know what the internet is, we don't know what, Code Academy is, or boot camps, or like, HTML, or anything like URLs, like high speed internet, HTTPS, like secure socket layer. Like they're just like, what is cybersecurity? Like you're a fucking mad person, mad woman, mad. I said mood. You're fucking nuts. You're just, it's drivel to them. But the only algorithm that you can remember these concepts. But in terms of mathematically, there's one algorithm of all algorithms that exist. You can remember one algorithm. And it is union find. Now, why? Why union find? Because think of it in the way that I've thought about it. Now, I have this book here. Let me pull it out. I have this book. I bought it some years ago. And this book is titled The Secrets of Mental Math. And it's from the Great Courses series. And it's by Professor Arthur T. Benjamin of Harvey Mudd College. And they talk about the Vedic method. And it goes on to say on the back that Professor Arthur T. Benjamin is, quote, an engaging, entertaining, and insightful professor of mathematics at Harvey Mudd College. He has been reportedly honored by the Mathematical Association of America and has been featured in Scientific American, the New York Times, and Reader's Digest, which named him America's best math whiz. Point is this: union find method. Look, America, the union, gotta find it. When you travel through hyperspace, of all algorithms, if you can only remember one, and I learned this through Princeton University, the union find method. It's a real algorithm. Look it up. I'm not making it up. Don't take my word for it. And I remember it because when I think of Project Pegasus and all these different stories like John Teeter that people say are mere fabrications, this, and that, well, those are opinions of folks. Albeit, if you do time travel, who knows where you might travel to? The land of Torrid. Just saying. Somewhere around Spain. I don't know. It's called Torrid in another universe. And there might not be a United States. So you might have to find the Union because it's something other than America or USA, United States of America. And landforms, land masses, things have changed. I'm just simply saying. So, union find method, displacement, fuzzy logic, fuzziness of displacement, amplitude, time travel. All right, what does this say here? Using LaTeX. All right, LaTeX was back in 1994, 95. It was an emerging technology in which to display the typesetting of mathematical information. If you're going to publish any scholarly information on the subject of mathematics and use mathematical algorithms and formulae, you will most likely be using LaTeX. Now, people will pronounce it differently. Some will say LaTeX, but it is cautioned against saying anything similar to, relating to, pertaining to latex, like a prophylactic rubber. Often you'll hear LaTeX or LaTeX, but it's not latex, okay? So get that out of your mind for those of you who think dirty. All right, particle wave duality. What's a particle? Is it a particle? Is it a wave? Is it a wave? Is it a particle? My math mentor often talked about particle wave duality. Then you have Avogadro's number, Fermat's last theorem, the eternal braid, which I read this book, Gödel, Escher, Bach, and I believe it's something like The Search for the Eternal Golden Braid. There is Dirac. He talked about a cellular automata. I already mentioned Minkowski Space. Looks like modular arithmetic and modular functions. axioms, paradoxes, mathematical models, modality, subspaces, Green's theorem, Stokes' theorem, +1, -1. Let's see, what is this? That's the fundamental theory of calculus. Then you have Cauchy sequences, which is spelled Cauchy. Some will say Cauchy or Kachi. Pronunciation that I have seen and heard and observed is Cauchy sequences. And then finally, also limits. Limits are very important. Limits. The notion, what year was this? Let's see, my math professor, mentor, he and I left off slightly after he was married with wife and children. What was that? In the early 2000s? He had mentioned that after he had been traveling the world, that he had been studying with industry, that is mathematical industry, the concept of metastability. Metastability. So in 31 minutes, 9 seconds, what have you learned from one Sir Grove? I've been a math teacher, highly paid, college honor student, was in a math degree program. 99% of my students became honor roll students. I was formally trained under the tutelage of my math mentor, professor. And I have discussed basic to intermediate to advanced mathematical concepts, all within 32 minutes and 8, 9, 10 seconds. If you go to YouTube, which this podcast is also imaged over to podcast, I don't really see a lot of what I discussed put into perspective in the way that I put it into perspective, which is why I took the time today to get my notes right. Linear optimization problems. Optimization problems. What does this say? Displacement problems, amplitude, norms, values. What is this? Euler equation and theorems describe the system. Viewing, understanding. What did I write here? Math with an adult mind. Yes. With your adult mind, it is easier a lot of times to understand intermediate to advanced math concepts because it just makes more sense when you're an adult. I had a president of my school who later became a dean provost, and he is a black African-American gentleman, married, wife, and he is also fluent in German. And what he was saying was that though math is kind of sort of a mystery to him, perplexes and puzzles him, he nonetheless, with his PhD and master's in German, higher education, he is able to understand mathematics now, which is 15 years ago, more so than he did when he was in college. So those of you who don't have a college and beyond math background, I'm saying intermediate to advanced, I went through the various concept, principles, topics of math and simplified them on some level so as to better present that information to you. What does it say here? Math should not be hard or difficult versus rigor. We sometimes and often talk about the rigors of math. The rigors of math. Because math can be rigorous. Simplified, looking at everything from discrete, calculus to circuits, electronics, since high school, clarification, terms, terminology, equation or theorem to describe the system, Viewing, understanding. Okay, we already said that with the adult mind. Provost said under, we already talked about that. Math is pipes, integration by parts. Types of calculus, we already talked about that. Differential calculus, integral calculus, what's above the graph and what's below the graph. Also, don't overthink math. Do not overthink math. Overthinking math leads to math anxiety. If you have math anxiety, then I want you to dial it back, step back, and just say to yourself, I'm overthinking this and I need to stop. From this point forward, I will not overthink math. Therefore, I will not have math anxiety. If I ever had math anxiety, it ceases to exist. And if I am thinking that in the future, that is, I have trepidation that I will have math. If I am thinking I have trepidation that I will at some point in the future have math anxiety, it is eliminated and I will not have math anxiety at any point in the future ever. Okay, I want you to get that out of your mind. Neuro-linguistic programming, NLP, Once Grove says so. All right, let me see. What does this say? Clarification of terminology. All right, we've already done that. We already talked about that. Let's see. Forest, trial spaces, triangular numbers, Bray, Jacobian, Euler, Fermat's theorem, Dirac, Archimedes spiral. Avogadro's number, Fermi paradox, and then there's the Casimir effect and Compton effect. What does this say? Antipode, bifurcation. My math mentor, Professor Math, also often talked about bifurcation. I'm looking at packets, branch circuit, linearization. Again, talking about optimization problems. Something is either linear or non-linear. It's either continuous or non-continuous discrete. If it's discrete, then it doesn't repeat. It's just discrete. It's just one data set that ends and terminates and does not continue forward. So let's then look at, where are my discrete? Let me see. Discrete versus random, continuous random variables. Okay, so continuous random variables. And then I said yes with like a thumbs up and an exclamation point mark. So when we're talking about continuous random variables, we're talking about measuring. Now just bear with me. Two data sets. Continuous random variables, measuring, versus discrete mathematics, which is counting. So again, discrete mathematics, which terminates, is not continuous, it ends. That's why it's discrete. It's just like over here, this little package is like, okay, ends, okay, doesn't continue forward. That's known as counting. When you're talking about continuous random, which can be anything, random, pseudo-random variables, then you're talking about measuring. Then I see over here Henry. If you're talking about Henrys, Pascals, Joules, Debye's, we're looking at differentiation, integration again, area under the curve. You have stochastic processes, wave-particle duality, paradoxes, advanced topics, Fourier, Poisson distribution, Lagrange optimization, set theory, P as in Papa of X as in X-ray. And then what else? I think that's pretty much it. Riemann sums. My math mentor often talked about Riemann sums, Hamiltonian, martingale, golden braid spiral, Archimedes spiral, galaxy. Oh, Gaussian. Definitely Gaussian. El-Gamal, Hermitian, Galois. What does this say? Annuity. Limits again. And then, what is that? Fermi, delta, sigma, tau, rho, lambda. Let's see. Riemann sums, I've already discussed that. Displacement, area, volume, plus other for integral. Integral calculus assigns number to f of x. All right. Okay, we already talked about that. And then switching, multiplexing, antipode, VDS squared, Debye, interpolation, rate of change, strings, dots. What does this say? Oh, anode, root, forest trees, geospatial physics math. Yeah, so that pretty much covers. Oh, here's de Rham, Dirac, Fermat, eternal, golden braid, Poisson again, atomic number, electron, proton, atomic mass, proton, neutron. Let's see, losses, electrons becomes or equals positive charge, either positive or negative change, charge, atom, rate of change, difference of, let's see, arc, tau, sigma, lambda, Zener diode, potentiometer, remainder theorem, standard deviation, logic gate in, K-1, R sub C, isotope difference, what does that say? Number of lambda, 1 over x, x over 1, 1 over x, y over, no, I'm sorry, 1 over x, x over 1, y over 1, y over x plus 1, y plus x ions. So the output in a function, y, total amount, x, independent variable, input to the output, funnel, calculus, f of x, g of f of x. The point is, in 42 minutes and 4 seconds, we covered a broad range of topics in mathematics. I am one Sir Grove. This is what we do at C4CW, casting 495 celebrities worldwide, private military company, defense contractors, entertainers, media personalities, celebrities. Thank you, the audience, for tuning in to yet another episode. One, peace.